Hi there and welcome to the screencast for Workshop 4. So I'm going to start by loading it up. And you can see that I've been prompted to install a few packages. So I'm going to click install on there. These are the R sample and the yardstick package, which are from Tidy Models. So it's going to go away and install all of these for me. This will probably be faster on your computer because you're most likely on a Mac or a Windows box. And so you'll be downloading pre-compiled packages, whereas I'm on Linux, and so it's building from source, which takes a bit longer for some packages. Okay, and we're done. So today we're looking at prediction, and we're going to start with a model that we all should be familiar with, which is the linear model, or the linear standard multivariate regression model. And it's sort of the perfect model to start with because it's something that we're already familiar with, and so not much here will be new other than sort of the angle that we take. So in data mining, we're most interested in prediction. We're not so much interested in explaining what's happening necessarily. Sometimes you might be interested in explaining things, but many of the models that we're going to be using will be somewhat black box in nature, some of them more black box than others. And so we may not be able to explain what's going on in the model. All we'll be able to do is sort of measure how well we do at predicting an outcome. So in this case, we've got some data on, some quite old data on a very old computer, the Sun Spark Station, running in a university department. And we've got all of these variables, which are all to do with essentially the computation performance of the server. And we're looking to predict the user function, which is the percentage time that the CPUs run in user mode, which is basically how busy the computer is essentially, as a function of all these other variables. And I think they're all, in this case, numeric measures. So we're going to be loading some packages. So there's a few new ones here, R sample, Broom, and Yardstick. So you may need to install those first, and then we read in our data. So let's have a quick look at it first. You can see that it's essentially numeric across all the columns, I think. Yes. So we're interested in predicting this column, the user column here, based on all of the other data in the other columns. Okay. I think it's complete. I don't think there's any missing values, so I don't think we need to necessarily worry about that. Seems to be reasonably complete from what I can see. Of course, we could test that, couldn't we, just by visualizing it. So if we go viz missing, we're going to need that from the Narnia package. We could get an idea, and yeah, so everything's there. Okay, the other way we could do that, of course, is we could do comp filter complete cases, and we see we still get 800 rows. Okay, so everything is there, which is great. Okay, so let's start by looking at the data using Skimmer. And so you can see here we've got 22 numeric variables, and there they are there. You can see that they're on all very different scales, which for the linear model is not a problem, but for some of the other models that we deal with, that would be a problem. Mostly from a computational perspective. So when we look at neural networks, we'll see that computationally you want them all on the same scale. Otherwise, you just get issues in the computer. Many of them are skew. So we can see here that the distributions are all skew to the right. But again, that's not necessarily a problem. So for the linear regression model, what we're interested in is the distribution of the residuals. And so even though our measure here, user, which is that's the last row there, is our outcome variable, is skewed to the left, that's not necessarily a problem. What we're looking for is whether the residuals are relatively normal or not. Okay, so to get a feel for how the target variable varies with each predictor, we could do pairwise scatterplots. Because these are all numeric, we could do scatterplots of one variable versus the other. So for example, this is the LRead variable, the very first one, versus the user variable, and you can see that there's possibly some information there. So we've got a few outliers here, but you can see that it seems to be mostly a decreasing trend, right? And it's potentially reasonably linear, although the variation around the trend is quite strong at higher values. So potentially a transformation on the lread variable might be useful. And we could do that for all of them, right? We could alter it to what's the next variable, lwrite, and just sort of investigate them one by one to get a feel for, and this has a similar sort of relationship. We might try transforming it maybe, just to see what happens. So put the x variable there on the log scale. Yeah, so you can see here that maybe that would be a sensible transformation to do. One thing we do have to worry about is that there's obviously some zeros here. So when we let log transform them, we're getting infinite values on the continuous x-axis. So we might want to do something like log 1p, which it doesn't actually have that. So there's a transformation that you can do which sort of adds 1 to the lwrite. So if I add 1 manually here and then do the scale log 10, it will, we don't get that same error because we're no longer mapping 0, no longer taking the log of 0, right? Log of 0 is minus infinity. We're no longer taking that, where our smallest number that lwrite can be is 1, and log of 1 is 0, right? So that's often a way we get around that problem when we're doing log transformations. Now we're not going to look at log transformations any further, but it's something that we could do. So let me just restore the code to what it was for the solutions. So we'll just do that one, and then we'll maybe do this one. Okay. Right, so this is going to take a long time to do, right? So another way to take care of this is to utilize, to essentially combine all of these different measures into a single column. So we're going to force the data into an untidy form. So we're going to, instead of having 21 columns plus the outcome, we're going to have 2 columns, one for the name of the variable and one for its measure, and then the outcome variable. Right, so this is going to be very untidy because we've got multiple rows for one observation, but it will allow us to plot things very efficiently. Okay, so that's what this next code does. What we do is we're going to add a row identifier. So let's see what that does. Okay, so when we do that, we get this extra column for the row ID, and that's just so that we can go back again easily to this format. And then we're going to pivot longer, and we're going to take every column except the user column and the ID column that we've just added. So that's going to be all the other ones. That's going to be all of these 21 columns here. So we're going to pivot all those longer. The names 2 is just going to be name, and the values 2 is going to be value. So let's run that and see what happens. Okay, so here you can see that for row ID 1, we've got now 21 rows, right? There's the last one there, row 21, with ID 1, and of course each of those rows corresponds to a different variable in the original data. So this is not tidy in the sense of tidy data, right? Tidy data should have a single row for each observation and single columns for each variable, but now we have multiple rows, 21 rows for one observation, and the variable names have been put into the name column. The advantage of doing this is it's very easy to plot it now, right? So we've got a single variable here for our that we can use as our x variable against our y variable of user, and then we could facet by this variable to split them up again, right? So we could get essentially one plot of lread versus user and another plot of lwrite versus user done automatically in one call. Okay, right, so let's try this ourselves. So the first thing is, can we go back to the original data? So can we go from this long form back to the original data? And of course you should be able to. All we need to do is pivot from these two back to the original. Okay, so we should just be able to take comp long and pivot wider, and we'll just take our names from the names column and our values from the value column. Okay, and that should give us the original data plus the addition of the ID column. Okay, so if we go across here, we'll have our user column. Yeah, so the only thing that's happened is that the user column's in a different place than it was before, so it's second. Okay, now you might be wondering whether this is actually exactly the same as the previous data frame, and we know it's not because the order of the columns might be different. In this case, it's only the addition, so we've got the addition of the ID column and the location of the user column is different. But one way to check whether two data frames are the same, even if the columns may differ in order, or the rows may differ in order, instead of trying to get them into the right order in order to do a comparison, we can use the dplyr joins for this, right? So we can use an anti-join to check this. So if we go comp wide and anti-join to comp, what this will be doing is it will be saying, are there any rows? So it does the join, so any of the columns that are shared between comp wide and comp, it will use to join them together. And then it's saying, are there any rows in comp wide that are not in comp? Okay, and you can see here, oh, whoops, we didn't actually we didn't save that, did we? Let's call that comp wide. Save that, spit it out so we can look at it. There we go. And now we can run this one here. And so you can see here that we have, so it's joined by all of the columns, except for the ID column, because of course the comp doesn't have the ID column. And it's returned 0 rows, right? So no rows returned. So every row in comp wide is in comp. We could try the other way around. And again, no rows are returned. Every row in comp is in comp wide, right? So we can conclude from this that comp wide and comp have the same number of rows, have the same rows. What we can't confirm is that they have the same columns. Okay, but of course we can tell that also because of the join list, right? You can see it's joined on 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So it's joined on 22 columns, and of course comp had 22 columns. So we know that all of the columns in comp are in comp wide. And all of the columns in comp wide are in comp, except the ID column. So they must be the same. Okay. So that's a nice way of checking whether two data frames are essentially the same without having to worry about the order, right? So many of the things in of the commands in dplyr don't necessarily have to maintain order. They generally do. So most of the time things are ordered, are left in order when you process them, but they don't have to be. So for example, there was no reason that when we pivoted longer that lread followed by lwrite followed by scall was the order that these ended up in, right? Because there's no constraint on that, and it could have instead done them alphabetically or something, right? There's nothing wrong with that. It still would have been the exact same form, it just would have had a different order. Okay, so one thing you can't be sure of, particularly when you go past just reading in from a CSV file and you start dealing with databases, you can't be sure that the order you're going to get is the order that it is in the database necessarily, okay, because there is no guarantee on that. Obviously we have tools to rearrange things if we need to. Okay, so what was the whole point of putting it in long form? The whole point was was to be able to do graphs, right? So you can see this down in part 3 here. Now that we've got comp long, we can use ggplot to produce scatterplots of user against each of the variables, right? So all we do is we go ggplot on comp long, right? So let's data equals, make our code self-documenting if we can. So we're going to do a scatterplot where we're mapping x to be the value column, right, which is the values across all our variables. Right, let's look at comp long again. It's this column here versus the user column, and then we're going to break them up with the name column. Okay, so our y variable is going to be user. So if we just run that, of course, we'll get a scatterplot with all of the different variables on it. So like this block here will probably be one of the variables, and this block up here will be another one, and there'll be a whole bunch of them on top of each other down here. And then we're going to facet wrap by our name variable. Name, not names. Okay, and there we go. So you can see that out of the box this isn't particularly useful, mostly because these variables are on different scales, right? So we want the individual scale for each of these variables to be different. So we're going to scale equals 3x, right? The y variable we want to be the same because that's of course the user variable, which will be on the same scale. And maybe I'm going to add some alpha in here because we've got quite a few points, don't we? There we go. All right, so that's one way to get all of the variables plotted at once. Okay, so it's very simple. We do pivot longer and then throw it into ggplot and facet wrap by that names variable. Now, a wee shortcut is that when we did the pivot longer here, we specified the names to and the values to. You don't have to do that if you're happy with them. So for example, that you see that the default for the names to in the pivot longer function is name, and the default for the values to is value. So we could just actually get rid of those altogether. We also don't necessarily need the row ID to column. That's just so that we could get back again to the wide form, to the tidy form. Okay. If we're not concerned with going back and we're just concerned with visualizing the data, we don't need that first command. So all you need to do is say pivot longer and take out the column that you don't want pivoted. Okay. And then throw it straight into ggplot. Okay, so what we can see from there is there's some variables that are very strongly related to the user variable, the pflt, the fork, the vflt, for example, the scall, sread seem to be mostly nicely associated, and they seem to be mostly linear, right? So a linear regression model on these variables is going to, you'd think would tell us a reasonable amount about the user variable. Some of the other ones are less obvious, like these ones here. Perhaps they could do with the transformation first before we go and do it, and you can see this free swap thing, which is the amount of swap space, swap memory on the computer. So that's it's essentially that's space on a slow disk, for example, a hard disk. These days it'll probably be on an SSD, so it would be probably reasonably fast anyway. But it's slower memory than RAM. And this, of course, is free memory here. Page free is something to do with memory as well. It's a number of pages, number of memory pages that are free, I think. Anyway, there's definitions for these if you want to look at the data set. Okay, so we could write a little bit about this here. Some of these variables, e.g. pflt, which other ones? Scall, sread, swrite, vflt, seem to have information can be used to predict user, and the relationships seem to be relatively linear. Straight line. So a linear regression should do okay here. Right. Right, so we're going to go on and we're going to model this data with a linear regression. But before we do so, what we're going to need is we're going to need a way to measure how good our fit is. Okay, and what we want to do that measuring is we want an independent set. Right, so we don't want to measure the performance of the model on the data that we use to train the model, to build the model. And the reason is that the data that we use to build the model knows everything it needs to know about that data in order to fit it as well as it possibly can. Okay, and so if we evaluate the model fit on the data that we've used to fit the model, then we'll get an unrealistically small error. So we'll get an unrealistically good measure of how well the model is doing, because of course the model's seen all that data. It should be able to predict it really well because that's data that it's seen. What we want to know is how well will the model do on data that it hasn't seen. Okay, so we want to avoid home ground advantage. So our goal is then to split the data into our 800 rows here into two sets. So we're going to use 3/4 of it, so 600 rows as a training set and 1/4 as a test set. So it's 200 rows. And so that's how we're going to go about it. Right, so the idea being that we train it on the 600 rows, we give it a bit more data in the training set because we want our model to be reasonably well trained. So that's why we're using 3/4 of the data in the training set. But we're going to hold out, we're going to take 200 rows that the model will not see, and that's what we're going to use to assess our model performance. Okay, so we're going to fit model on the 600 rows, and then we're going to predict what the outcome variable is on the 200 rows that the model hasn't seen, and then we're going to compare its predictions with the actual value of the user, the target. So we could, of course, just take the first 600 rows here. So we could just take rows 1 through 600, and that's the rows that we choose. Okay. Now you should know that you should realize that that's probably a dumb idea, and the reason is that the order that things have been put into the file here might be important. Like, for example, they might have been put in order of user, for example. It doesn't look as though that's the case here. It looks relatively random, but because we don't know that, we want to ensure that we randomize the data first before we pick out those 600 rows. So one way we could do it is we could just randomize the order of the rows and then take the first 600. That would be completely valid. But of course there's tools to do this, and we should use the tools that are available to us. So the initial split command from the rsample package, the rsample package is essentially being developed purely for the purpose of sampling from a data frame, or resampling from a data frame. And that's of course what we want to do. So it has a function called initial split, which takes a data frame and a proportion. Okay, so the proportion here is the proportion that you want in the training section or the analysis section of the data. Notice that I've set the random seed here, just so that this is reproducible, i.e. you will get the same split that I will. Okay, that's generally advisable, just so that you can make sure that anything that you're then seeing from now on is not dependent on the random number, the state of the random number generator when you started. Okay, often it's useful to, particularly when we're training lots of models later on and we're comparing models later on, you may well find that several models give you similar sort of predictions. Okay, and so varying the random seed that you use may then allow you to then refit the same models, just basically rerun your code with a different random seed. And if you find that the order of the models, so which one is best, sort of jumps around a bit, and so different models tend to be best depending on the random seed, that's basically telling you that there's a lot of randomness in your ranking of the models. Therefore, several of the models are equally good. Okay. Right, so let's start by splitting the data, and you can see that the split object basically just tells us how much is going to be in the analysis or training set, how much is going to be in the assessment or test set, and how much is going to be total. And this is, so the split object here has stored the data as well as which rows should be assigned to the analysis and which rows should be assigned to the assess test, and of course that assignment has been done randomly. Okay. Now we can look at it by using the tidy command. So the tidy command is a generic. It's part of Broom, and it can apply to many different types of objects. And so in this case, you can see that this just basically tells us what the which rows are in the analysis set and which rows are in the assessment set. So you can see that row 1 and 2 are in the analysis set, row 4, 8, 10, 11, 12, 13, 14, 15, etc. are in the analysis set, and of course eventually if we go down to row 600 or whatever, we'll see where it changes. That'll be here, won't it? So these are, here we go, there's the analysis sets, and then row 3, 5, 6, 7, 9 and so on are in the assessment set. So it's allocated them randomly. Alright, so, here we go, find the first row allocated to the assessment set. So we could do that easily enough, couldn't we? We could just take this data frame and just filter such that the data column is equal to assessment. Alright, so there it is, there, row 3. Alright, my computer is doing weird things with the... So let me restart, reopen that. Okay, where are we up to? Yeah, done. Right. Check we have 600 analysis and 200 assessment rows. Right, that's easy enough. What we could do is we could take our tidied data, tidied split data, and we could just count the data column. So sure enough, we've got 600 analysis rows and 200 assessment rows. Okay, so initial split is the way that you split data up. Okay, and you can vary their proportion. So generally it's advisable. So 3/4 I think is the default and is a reasonable value to start with. Okay, but there's not really any particular reason why 3/4 is better than 80% or half or whatever. Generally you do want more data in your training set, but if you've got lots and lots of data, then of course that's slightly less important. You know, if I've got 1 million observations, then it probably doesn't matter too much if I have 500,000 in my training set or 600,000 in my training set. I've still got lots and lots of data. And of course you don't want too few observations in your test set, because that's what you're going to be using to assess model fit. Okay, so now that we've done our split, this hasn't actually returned the data sets that we want to then use for modeling. We need to pull them out of the split. So the training and testing functions pulls them out. So you can see that the comp train now has the 600 observations on 22 variables, and comp test has the 200 observations. So comp train is our training set, and comp test is our assessment or test set. And these of course should look quite similar because we generated them at random with a random split. So hopefully once we train a model on comp train, we should do reasonably well at predicting on comp test. Okay, so we're going to start by fitting a linear model for the user variable in terms of all others. And if it's been a while since you've done linear modeling in R, you remember that the formula syntax here is how you set up the model formula, and the dot is short for, or the period there is short for, all other variables. So here we're fitting a linear model or a multivariate regression for the outcome variable user in terms of all other variables. So let's run that. The summary command, we save the output of LM into the model1 object, and the summary command then gives us the usual sort of summary for a linear model. We get our estimated coefficients of the linear model. All right, so there are the numbers to multiply each of these variables by, add them all up to get the outcome. We get their standard error, so that's the uncertainty in these estimates. And of course we get a t-value and a p-value, which is for the hypothesis test that these things are 0. So you can see that some of them are close to 0. So this is 0.008. And because of the amount of uncertainty, you can see we've got more uncertainty here than we do have in the value itself. So therefore the t-value is low, and therefore the p-value is high. Right, so there's a good amount of chance here that what we saw in our analysis set here of the effect of PPG out on user after controlling for all the other variables is essentially meaningless. Whereas some of the other variables are highly important. So exec, for example, is highly important. scall is highly important. And pflt is highly important. After controlling for those, vflt is also important, free swap is important, and so on, okay, because they have low p-values. But not all the variables are important. And you can see that overall model fit is pretty good. We've got a multiple R squared of 9.93, so that means that 93% of the variation in the user variable is explained by the variables that we have in our model. So this is so only 7% of the variation in user is unexplained. So this is pretty good. Now there's a couple of helpers in the Broom package that sort of make this data a little bit more usable for charting. So there's essentially three main things in the Broom package that you need to remember. There's tidy, which we've already seen. Let's see what that does. We'll do that down here. There's glance, which is this one here. And then there is augment, so which we'll see later as well. So glance basically gives us the information down the bottom here in a tidy form. So we've got a data frame. It tells us what R squared is here. There's the adjusted R squared, which is basically the multiple R squared adjusted for how many variables we've got. Sigma is the estimate of the variance of the residuals, or the standard deviation of the residuals. The statistic here is the F statistic. The p-value is the overall p-value, and the degrees of freedom are 21, and these are the degrees of freedom of the residuals. These are the number of observations and the log likelihood and some information criteria and deviance. Okay, these are essentially all model fit information. So we'll see the AIC later on when we do stepwise regression. Okay, so let's check that we remember some things about linear modeling. How many predictors are included in model 1? So we can know that all the columns other than user are in the model. So that is 21 predictors. Right, there were 22 columns and we've got 21 predictors. We could also just count them here. I'm precluding the intercept because that, of course, would be in the model even if we had no predictors. That's just sort of the baseline. Just calibrating where to start on the user scale. Okay, which predictors don't seem to be providing much information? Well, we can just do this with the summary table, can't we? So let's see. L-read doesn't really provide much information. What other ones? Fork. Char doesn't seem to be super important. Right, just because they have high p-values. Page out, and PG out. Which other ones? Etch and Pigeon. Any others? Let's have a look. Those are the ones that definitely aren't important. As their p-values are large. Right, I'm just going to make these look a bit nicer in when we render to HTML, just by surrounding them with backticks. Okay, try using tidy from the Broom package to get a tidy summary. All right, so tidy model 1. So tidy gives us a tibble, a data frame, which is equivalent to the coefficients, right? So we get one row per term. We get the estimate column, standard error, the statistic, which in this case is our t statistic, and the p-value. And the nice thing about this, of course, is we could have easily answered this question with code. All right, so we could, for example, for example, go tidy model 1, and then we could filter p-value greater than 0.2, for example. And so you can see here that lread, fork, rchar, pigout, pipigout, atch, and pigeon are all unimportant, which is this list here. Okay, so that's an easy way of answering that question. Okay, so we fit a model, and it seems to be relatively good at prediction. Now what we want to do is evaluate the actual predictive performance by using our test set. Okay, so there's two ways of doing that. I'm just going to look up the help for augment because I think I might have got that wrong. No, it is new data. Okay. I seem to remember with tidy models that's new underscore data, but we'll get to that later. Okay, so what are we doing here? We're using the Broom model here, the Broom package to do prediction. So we could just use predict. So before we start looking at the augment function, we could just use predict just to see what this does. So we could take model 1 and we could just run predict on it with some new data. So first of all, let's run it as is. So predict by default will spit out a vector of predictions, model predictions, and you can see there's 600 of them. These are predictions on the training data. So this is essentially the fitted value on the training data. We could also do predict on new data. We could ask it to predict on the comp test data, and you can see now that it has 200 predictions, one for each row in the comp test data. Now this is a vector that it spit out. It's not a data frame. But predict can also do prediction intervals. So for example, if I do interval equals prediction, so this essentially is our prediction in this column here. Those are the same numbers we had before, but it's also got a lower and upper prediction interval, and these are is basically 95% of the time we would expect the truth to lie within these intervals. Okay, so this is essentially a measure of how much we think we might be out. So this is our best guess at what row 152 should be, but it should vary from 92.4 to 99.7. So the truth probably lies somewhere in here, or at least we're 95% confident that given the value of the covariates at line 152, the user variable is between 92.4 and 99.7. Now the problem, of course, with this is that this here is a matrix, and previously it was a vector. So we're getting different output conditional on the input that we put in, a different output variable type. And so the predict function is unpredictable to us, right? In that we can't easily predict what the output variable type will be. So for example, if I saved this object in D, right, and I run dim on D, I get null. Whereas if I add the prediction interval, interval equals prediction, then I run dim on it, then I get something, right? Because it's a matrix now, and dim makes sense for a matrix. It doesn't make sense for a vector. Similarly, if I use length, right, I get 600 if I've got the interval equals prediction, but if I remove that, I get 200, right? The length is unpredictable. And that's not really a good thing. It's not really a good characteristic of an API, of a function call. And the reason is that I have to know what the function is going to return given the input variables that I give it. And at this stage, I would have to learn all of the different variations that Predict can give me in order to guarantee that that I know that I'm going to deal with the answer that it gives correctly. So, for example, what happens if comp test had some missing values in it? Right? If comp test had missing values in it, then of course it can't give me a prediction because it doesn't know what a particular column is. So in that case, is it going to return me an NA for the row, or is it just going to silently drop it? I seem to remember it silently drops it. Okay, so D ends up of length 199 instead of 200 if I had one row with missing values in it, and of course I don't know which row that is. And so if I just tried to paste them together, like add the prediction as another column in that data frame, I wouldn't be able to do it because they're different lengths. Okay, so so this is something that sort of plagues a lot of the R modeling tools, is that the predict function often has a similar syntax, but the thing you get out of it may not be similar. Okay, and that's one of the things that Broom, the Broom package, is intended to sweep up, to clean up, to tidy up. And that's why we're going to use the augment function if we can. Sometimes we'll be using predict, but often we'll be using augment. So I'll just write a little bit about that here. If you specify intervals prediction, okay, right, so the right, so, oops. Okay, so here we're doing augment. So it takes the same form as predict, right? So you get new data equals the comp test, but it returns a data frame, right? So it takes the comp test data and it augments it by adding some variables. So you can see here we've got the dot fitted variable, but we've also got some others. Okay, so you've got dot resid as well, which is the residual for that value, or the error for that value. If you do a prediction interval, it'll give you the prediction interval as extra columns, right? So the name of the column you get is always predictable. It's always dot fitted and dot resid, even across different model types, which is nice. And of course, it is a data frame. All the rows match up correctly, so everything works out of the box. So I can use select, for example, here to reorder things, right? So I'm pulling the user variable out and the fitted variable out just so that we can compare them. And you can see that the prediction seems to have done a reasonable job, right? There seems to be some sensible correlation between these two columns. Now from here, we can then use the mean square error to figure out how well this model is fitting. So the mean square error, it just takes the difference between the user and the fitted, squares it so that they're all positive, and then computes the mean. Right, so here's the computation here. Okay, so there's the mean square error, is about 6. And that could be useful to compare across different models. So at the moment, the number 6 isn't all that useful to us, although I'll show you how we can figure out what that means in a moment. But if we had 2 models, both with the mean square error, then we would favour the one with the smaller mean square error because that's the one with less error. So in terms of a regression model, you can see here this is the difference between the true value in the test data and the fitted value under the model, so that's the predicted value under the model, squared, and then we've computed the mean. So this is the mean square error, which is the same as the variance, near enough. Okay, so it's the variance of the errors. So the square root of this will be the standard deviation. So the square root of 6 would be the standard deviation. So what's square root of 6? About 2.45. Okay, so we'd expect to be most of the time within plus or minus 5. Okay, twice the standard deviation, right? So our prediction is getting us within plus or minus 5 of the truth, which probably isn't too bad for this variable. Okay. So alternatively, we could use the yardstick package. So the yardstick package is a package that's designed purely for assessing model performance, and it has a whole heap of different metrics for evaluating how close a model gets to the truth. Unfortunately, one of them isn't the mean square error. Instead, it uses the root mean square error. And the reason is that the root mean square error is on the same scale as the original data. So there it's just the square root of the MSE, right? Just what we computed before. So I could square that if I wanted to get the MSE. Okay. Right. So now that we have a measure, there's a whole bunch of other ones that we can use out of the yardstick package. We'll see some more as we go. Now what we want to do is compute a different model and use that to compare these. So we're going to look at a model with all predictors except L right, ATCH, S right, and page out. A model with just these 5, and then a model that results from using step to perform stepwise elimination. So right, so let's fit some more models. So we're going to go model 2, and we're going to do all our predictors minus, so data equals comp train, minus these ones. So I'm going to grab that list there. Right, so if you want to do a model with everything except a few, the easiest way to do it is to subtract them off. Might have been quicker just to write them by hand here, rather than copy and paste. There we go. So we could have a look at that model as well. Okay, so you can see we've got rid of some of the variables that aren't important. Our model explains still about the same amount, about 93% of the variation. So we've still got a pretty good model. Let's do the test. Work out the mean square error. So we'll do the predictions using augment on the test data, and then we'll use yardstick with root mean square error. Truth is going to be our user column, and our estimate is going to be our fitted column. So there we go. Our root mean square error with this model is better, right? So here's the model on the original, on this on our bigger model, and this is the model, the error here. So this is interesting. So interestingly, model 2, which is simpler, does a better job. on the test data than model 1, which was more complicated. And that may seem to be a bit counterintuitive, right? How can a simpler model give us better predictions? And it may just be that the uncertainty in model 1 had to include all of the uncertainty and all of the covariates, which, as we saw up here, was sometimes quite big. So we're including a whole heap of variables here that didn't really make a difference to the outcome variable. So we had to estimate them and include the uncertainty in those estimates in our predictions. Whereas in a simpler model, we did not. Okay, let's try another one. Okay, let's try one with these variables in it. So model 3. We're going to go LM on run QZZ plus free swap plus free mem plus PFLT plus our read. So we'll put a model on there. Let's take a look at it. Okay, so this is not as good, but you can see everything is highly important. So we're only explaining 83% of the variation here, so perhaps we may have simplified things too much. Let's see. So we'll augment our model 3 with our comp test data. And do our prediction assessment. So truth is user, estimate is fitted. So you can see here that we get a similar error to the full model. So this is actually it's slightly smaller, isn't it? So even this very simple model here is doing better than our big one. Okay, so that's interesting. And finally, a model that results from using step to perform stepwise elimination. Okay, so the last one we'll look at is we're going to take our first model and we're going to run step on it. So you recall from the lecture that stepwise regression uses the AIC to compare models. So the AIC is basically information criteria. So what it does is you start with the full model, you then remove each of the variables in tune. So we fit a model without PPG out, for example. We fit a model without PG out. And for each one, you compute the AIC, which is the information criteria. The AIC is basically, it's a measure of model fit, which is the log likelihood, minus a penalty term for how complex the model is. So you're trying to trade off model fit with model complexity. Okay. None here is the full model. And so you can see that removing PPG in makes the AIC worse, bigger, whereas removing L read makes the AIC smaller. And removing PPG out makes the AIC the smallest. And so after checking each of the variables in turn, we're going to go by removing PPG out. So you can see in the second model, PPG out is not listed. And then we repeat the process, right? So we've got only 20 predictors here instead of 21, and we remove them one by one and see which variable, when we remove it, results in the lowest AIC, which again is PG out instead of PPG out, and so on and so forth. And you complete the process. You can keep going until you can remove no more variables. So you can see here that in this step, we've reduced it down to this set of predictors. And we could remove, we're going to be removing our read. And it's also saying that we could remove ATCH and get an improvement in an AIC as well. But once we've removed L read, we can see that removing ATCH after that is then not so good. So our final model is this one here. So let's assess how well that does. So we'll take, is up to model 4 or 5? Good question. It's model 4. Okay, so we're going to do our predictions. Model 4. Okay, and then we'll do our model evaluation. Okay, so here we have we've improved things, but not as much as that second model. So the best model appears to be model 2, which had the lowest root mean square error. That would be the one that we go on with for further modeling. Okay, there's lots of other things we could try. We could try transforming variables and fitting models and so on and so forth. We could mess about a bit further with the model 2 if we want to. So now we're going to finish by having a little closer look at the predictions from the original model. So you remember that the root mean square error was about 2.4, right? Which is about a measure of the standard deviation of the error in the user variable. But if we have a look at the standard deviation of the user variable, it's actually only 7, right? So that seems a bit strange because our model was such a good fit, right? Our model was explaining 93% of the variation in the user variable, yet we've only managed to reduce the standard deviation by about 2/3. 2/3 is quite different to 90%. So, for example, if we compute the variance instead, right, the variance would of course be the squared. So the variance here is going to be 49 of the user variable, and the variance after building our model is 6. Right, so we've actually shrunk the variance from 49 down to about 6 or so, but that's not a reduction of over 90%. It's only a reduction of about 80% or something, right? So what's going on here? Let's take a look at our model predictions, and we're going to plot the predictions. So here's our predictions in fitted, and here's our truth. And what we do see is we see an immediate issue here, where there's one very strong outlier, which has a relatively low user variable, but a very, very high prediction. Okay, so this entry has a very large error, and it probably has a large error because it has extreme values in the covariates. So for example, we could find that one if we have a look at it. Right, how could we find that? Well, it's the one where the user variable is less than 80, while the fitted variable is bigger than 90, right? So we could go model 1 prid, filter, user less than 80, and dot fitted bigger than 90. So there it is, there, row 76. Okay, row 74, sorry. And if we maybe go back to our plotting, we could compare row 74 compared to the others. So for example, what we could do is we could take, we could pivot longer, all of them except user and anything that starts with a dot. Right, so that's our fitted value and our residual. We don't want those either. I think that will work. We'll soon find out, won't we? Yep, that's worked, and then we will throw that into ggplot, plot points, where we're mapping our value versus our truth, and we'll colour it by whether the, now I need a row ID, don't I? Well, we could colour it by this constraint, couldn't we? It's a bit naff, but it'll work. And then we could facet wrap by the name variable, and of course turn our scales to 3x. So essentially what we're doing is we're doing that plot of user versus all the other variables, and we're just colouring by the condition here such that we get our observation just to see what might be going on. And we see here it is there. Jumps out like a sore thumb, right? It's got a very extreme L read. So because it had a very extreme L read, when we bung that into the linear model, it then had a very high prediction. And of course, because it is so extreme, the error here is so high, that's going to be magnified when we square it, as we do in the root mean square error. And so our root mean square error is magnified compared to what it might otherwise be, because we've got that strong outlier in it. Okay. Okay, so part of the reason that our root mean square error is inflated is because we've got this very strange observation, and perhaps some of the other measures in the yardstick package, such as the mean absolute error, might be better. So the mean absolute error is, instead of squaring the error, we take the absolute value. So we can compute this with summarize, right? So we take the user minus the fitted, take the absolute value and then the mean. Or we could just use the MAE function in using the yardstick package. So let's have a look at the mean absolute value of the other models. So we get model 1, MAE truth equals user estimate. So it's going to be model 1 predictions, isn't it? All right, and then we can just copy and paste that 4 times. All right, we'll run that and see how we go. All right, so model 1 is 1.6, model 2 is 1.48, model 3 is 2, model 4 is 1.56. So you can see here that model 2 is still doing best, but now model 3, which was better, is now worse. Okay, so model 2 is again the best. Okay, and just as a bonus, if you're interested, you could find out, you could try tuning the models a bit further and see if you can improve it more. And this is why the problematic row is in the test set. Let's grab that code that we did before and pop it down there. Okay, where is it? Code and put it down there so that it's in the tidy place. Okay, this is probably a better way to do it, isn't it? One way to do it is to find the problem row and add it into the training set with a new column labeling the row as a training or problem. That's probably a better way to do it, right? So instead of adding this condition in here, what we could do is, now that we've found it, what we could do is we could mutate and create a new variable, which is maybe type, which is going to be if else user less than 80 or dot fitted greater than 90, or and. That's a problem. Otherwise it's just training, right? So if we do that, then we could count the type column. Right, so we've got the one problem child, and the rest, maybe we'll just call them OK. Oh, okay, well that's another way to do it, I suppose. Add it to the training data. Anyway, let's do it slightly differently. Alright, so now we've got that, we can throw it into ggplot and color by type. And I messed that up somewhere, blah, blah, blah. Oh, we need to pivot longer, don't we? Minus user, minus, here we go. And there's our problem child. Okay, and it'll be also a problem if you put it in the training data, right? So the other way to do it is instead of doing it with the Model 1 predictions, we could just use that filter in order to just get that one row in the test set, and we could then bind that using bind rows to the training data and do the same thing. So add the column as to whether it's training or whether it's the problem child, and then do the plot. Right, we'll just knit that, check it all works. Okay, that's looking good. Till next week.